Hey everyone, as I mentioned in class last Thursday, I'm going to swap out active learning, which was originally on the syllabus for this coming Tuesday, to after spring break because I think the first two application topics go together really nicely and I don't want a big gap there with spring break. And so on Tuesday, we're going to be talking about semantic and syntactic similarity, and that's what this lecture is about. And then we'll loop back to active learning sometime after spring break. All right, so this is the start of applications, and we're going to start with text applications. And so many tasks that you might want to do with text involve relationships between two or more texts. You might say, are two texts about the same topic or written by the same person? Does text A logically imply text B? That's a task called entailment. Which of a selection of texts is the answer to a question? Is text A a translation of text B? Which texts from a database are about a given query, etc.? And so one way that you could address the question of whether two texts belong together in some respect, they're the same text, one answers a question, etc. of the other, is to simply concatenate the pairs of texts with a separator token in between and run them through BERT, or your preferred large language model, and then use a classifier head. And you'll classify it as same or different. All right, so again, pretty straightforward. You have two pieces of text. You concatenate them, pass them through a transformer language model, an encoder, and then have a classifier head. So the advantage of this is that it allows cross-attention between the two texts, which often leads to more accurate results. And so when you're computing representations for text A, you can attend to text B and attend flexibly to whatever tokens in text B is most advantageous for the text at hand. So it kind of makes sense why this is going to give better representations. You know, if you want to know if two texts are the same in some way, are related, being able to have cross-attention between them is potentially very useful. However, it's often computationally infeasible to have cross-attention because if you have n texts, it requires embedding n squared pairs. So what if you have 10 million texts that you want to process? Well, then you'd have to push 10 to the 14th pairs of text through a large language model that potentially has 100 million of parameters, and that's just completely and totally infeasible. Not going to happen. So for a lot of problems that we care about, the scale of the problem doesn't work if we have n squared things that we need to embed. So it's just unrealistic. Another potential problem is that we may be interested in relationships between variable numbers of texts. And so we could just compute pairwise comparisons. But suppose that by doing that, we pass A and B through the encoder and we get A is the same as B. And then we pass text B and C through the encoder and we get text B is the same as text C. But then when we pass A and C through the encoder, we get that text A is different than text C, right? We have an intransitivity and you're going to have to deal with that somehow. So when you're interested in groups of things that are larger than two, but you're making all pairwise comparisons within the group, you can get these intransitivities that then indicate some kind of problem, and you're going to have a way to post-process them out, which just seems kind of pretty inelegant. And so a commonly used alternative is a bi-encoder model. And so we encode two texts separately. So we pass text A and text B through BERT or whatever transformer-based language model you prefer to use. And that's going to give us a representation for each of the tokens. Then those representations are pooled. So we just take the mean average representation because we need a fixed size representation, right? Like if a sentence has 5 tokens, there'll be 5 hidden states output for those tokens. If it has 7 tokens, there'll be 7 hidden states output. To compare those two sentences, we need a fixed size representation. Of course, you'll also recall that transformer large language models have a class token, but those class tokens don't work well for textual similarity, as you may recall us talking about from a couple of weeks ago. We talked about the geometry of the space and how kind of there's potential challenges there with using the pre-trained BERT embeddings. In any case, a major contribution of the sentence BERT paper is to show that just pooling the embeddings works better than using the class token. And because the BERT embeddings don't work great off the shelf, there's going to be some training data to train this to do the task at hand. And so we pass each sentence separately through a transformer large language model. We pool the resulting tokens, and then we calculate similarity, for example, by calculating the cosine similarity between those two representation vectors for those texts. And this is trained, as you can guess, using contrastive learning, which we saw in the course a couple of weeks ago. And so this has the advantage that you embed everything once. And then whatever comparisons you want to make, you just have to embed it once. So say you have some queries that you want to make of Wikipedia. You just embed Wikipedia once, and you can use those same embeddings for however many queries you have. And so therefore, if we want to compare in texts, we only need to embed in things, not in squared things, and that is going to be massively more computationally feasible as n becomes large, which often n is large when we're working with textual data. So why do we only have to embed things once? Well, when we contrastively train a bi-encoder model, as you'll maybe remember from the contrastive learning lecture, that's giving us this meaningful metric space because we've trained a space where things that are the same are nearby and things that are different are further apart. And so once we have this meaningful space where we're taking each text and mapping it into a meaningful vector space that's meaningful for our downstream tasks, then you can apply standard clustering algorithms over the embeddings. You could do classification by looking for their nearest neighbors and some other type of offline index. You can do dimensionality reduction to visualize the space. And so once you have this meaningful space, there's just lots of really cool things that you can do with it. And so generally speaking, there's two types of bi-encoder architectures. You can have a symmetric bi-encoder or an asymmetric bi-encoder. So symmetric bi-encoders fix the weights for both sides of the model to be the same. So there's only really, you are training these two bi-encoders to take two texts that are the same and map them to the same place, and two texts that are different and map them to different places. But the weights on both sides of that are fixed to be the same. So when you finish, you'll have a single model. So applications are usually used of symmetric bi-encoders are then usually deployed when all texts are of the same type. So things like semantic textual similarity, are these two texts saying the same thing, even though they're worded differently? So that would be something like detecting duplicate quora questions, topic clustering, etc. So you have kind of two types of text and they're of the same type. Asymmetric bi-encoders allow different weights for the two sides of the model. And these are usually used when there's two different types of text. So for example, for things like natural language inference or for retrieval, like on one side I have an encoder for encoding my query, and on the other side I have an encoder for encoding the first paragraphs of Wikipedia. Or an NLI, on one side I have an encoder for the premise, and on the other side I have an encoder for the hypothesis. There is a debate about whether, even if the two types of text are different, are you better kind of using symmetric models? But there's certainly contexts where the two types of text are quite different, and you might want to use an asymmetric model. Okay, so how would you train a bi-encoder? So your training data are pairs or groups of texts that have labels about the distance between those texts. So you could have continuous distances. More commonly, you might have cardinal discrete distances. So these two texts are the same or different. They're about the same topic or a different topic. They're about the same story or a different story, about the same entity or a different entity. You could also have ordinal distances. So B is closer to A than C is, where A is going to be your anchor in this case. Okay, so depending on the type of labels you have, that will determine your loss function. And again, this goes back to contrastive learning that we talked about a couple of weeks ago. You want to push the embedding of two texts closer together if they should be closer together, and pull them apart if they should be further apart. And so we need a loss function that penalizes the model if either of these things is not the case. And what the best loss function is going to depend on the labels you have and on your application. So cosine loss, the data are pairs of instances and a continuous label of the distance between them. For contrastive loss, your data is a list of input samples, each with a corresponding label among C classes. You have a function that converts that into an embedding. And so contrastive loss takes a pair of inputs and minimizes the embedding distance when they're from the same class, but maximizes the distance otherwise. So if these are the same entity, if text came from the same source, if it's about the same story, the same topic, etc., it's going to minimize that distance and otherwise maximize it, where epsilon is a hyperparameter that defines the lower bound distance between samples of different classes. You might use triplet loss, where you have one anchor example and a positive and a negative sample. The model will learn to minimize the distance between the anchor and the positive example and maximize the distance between the anchor and the negative example, where you have a margin parameter epsilon that's configured as the minimum offset between distances of positive versus negative pairs. To keep reviewing the contrastive loss functions, you might use supervised contrastive loss. So when we saw examples of this in the contrastive learning lecture a couple of weeks ago, we saw this in the context of images, which is where I believe it was first used, but you can equally use this loss function in the context of text or in multimodal context for that matter. So SupCon allows for multiple positives in batch. So given a set in image label pairs, two in-training pairs can be created by applying two random augmentations to every sample. You don't have to do the random augmentation part, but this was just part of the function in the original paper, but you could potentially drop that. Then you have the following loss function, which is going to maximize the similarity of the positive pairs and minimize the similarity of the negative pairs. Hard negatives, as we spent a lot of time talking about in the contrastive lecture, are again going to be important. We can't really have giant batch sizes even with text. So in your problem, you might have a way to explicitly find hard negatives. If you don't, you may need to mine for them, as we talked about a couple of weeks ago. Okay, so it's pretty common in the text space to combine a bi-encoder and a cross-encoder. And the idea is that you can get the best of both worlds by using the bi-encoder to create a short list of candidate pairs that you then pass to a cross-encoder. So I have a question that I want to ask of a query that I want to ask of Wikipedia. I have all of Wikipedia embedded offline, so I only have to embed it once. And then I embed my query, and I find the top 50 articles in Wikipedia that are the closest match to my query. And then I jointly embed my query with the first passage of Wikipedia for those 50 articles. I use that to re-rank those and find the ones that is most likely to contain my answer. We'll talk about that more next class when we talk about retrieval. The Sentence Transformers library has easy to use implementation for both bi-encoders and cross-encoders. They have bi-encoders and cross-encoders for a bunch of pre-trained language models. They have good documentation. In their baseline model, they've pre-trained the encoders for sentence similarity tasks like finding duplicate Quora questions and NLI. And so these models have been pre-trained to perform better off the shelf than you would get if you use just, say, BERT or Roberta embeddings, which have not been pre-trained for semantic similarity tests. And as we saw a couple of lectures ago, it's important to do that pre-training because the off-the-shelf BERT or Roberta, etc. embeddings don't do great. And so yeah, Sentence Transformers is just a really fantastic resource. The code base is highly optimized, it's clean, it's straightforward to implement. Okay, so now I want to talk about an application of these methods, which is detecting reproduced content in historical newspapers. And so I have a quote here from a media historian, Julia Warneri, who writes, by the 1910s and 1920s, most of the articles that Americans read in their local papers had either been bought or sold on the national news market. This constructed a broadly understood American way of life that would become a touchstone of U.S. domestic politics and international relations throughout the 20th century. Despite being important for a range of deep learning applications, text deduplication methods are overwhelmingly rule-based and tend to lead to poor results, at least on this particular problem. And so along with Emily Silcock, who's a pre-doc in our lab, and Luca D'Amico Wong, who's an undergrad at Harvard, and Jinglin Yang, who's now a first-year econ PhD student at Berkeley, we developed deep neural methods to detect reproduced articles and work that's forthcoming in ICLR. So the basic idea is that we contrastively train a model to detect which articles come from the same source in a context that's full of abridgment and OCR errors. And so there's some errors in the OCR, but also stories were rewritten by the regional bureaus of newswires like the Associated Press, and then they could be further rewritten and abridged by local newspapers to fit onto the page. And so you had these underlying newswire article sources, but the articles as they appear in local papers won't be exactly the same because there's abridgment and there's OCR errors. And this is a question that's actually of a lot of interest to people in the humanities, and there'd been a couple of different Ngram approaches before to try to solve this. But as you'll see, their performance is not that great. And so we want to contrastively train a model to detect which articles came from the same source in this context where there's a lot of abridgment and there's also OCR errors. And so this entails learning a mapping from the raw article text to dense vector representations of the article, where articles from the same source are nearby, even if they have been heavily abridged or have quite a few errors, and articles from different sources are further apart, even if they're articles from different news wires talking about the exact same event, even if one article is an update from another, so they're talking about the same thing and by the same wire, but one article is an updated version, those are further apart, because they're not from the same underlying source. So this is actually, it's a really challenging problem, and I think it blows my mind actually how well that you'll see the neural methods do on this. So we conceptualize this as a contrastive learning problem and train on a large data set of labeled article pairs. In order to extract articles that are from the same source, we're going to use single linkage clusterings on the embeddings that are produced by this contrastively trained model. So there's lots of different clustering algorithms. We use single linkage clustering because it's highly scalable, whereas things like hierarchical agglomerative clustering do not scale as well. We can add a re-ranking step that jointly embeds pairs of articles and classifies whether they're the same. So this is our training and evaluation data. So we have positive and negative article pairs that we've labeled for the training data and for a validation set for hyperparameters. And then we also labeled 3 full days, which were taken from the 1930s, the 1950s, the 1970s. Every newspaper in our corpus, for the front page of those newspapers and a sampling of interior pages, we labeled every single article that appeared that day. And so we're confident that that this is telling us how good we're really doing because we labeled everything that appeared on the front page on those 3 days. And so overall, when you combine the training and the validation data, we have over 122,000 positive pairs. Of course, we're only going to use about 36,000 of those in training. We have a massive number of negative pairs, right? Because we labeled every article on 3 days, and n squared is a big number. But obviously, we're not going to be using most of those negatives in training. In the training data, we have, I believe, about half of our negatives that consist of hard negatives, where we had explicitly labeled articles that are, about the same thing from a different wire or updates to provide hard negatives, and then the rest of them are random negatives. And so in our database, there's a total of over 27,000 articles. And so these are the results of the neural versus the non-neural methods. So the bi-encoder has an adjusted RAND index of 91.5. The adjusted RAND index is a measure of accuracy and clustering, where essentially 0 is how you would do randomly. And that's important, right? Because when everything's negative, right, even randomly, your accuracy might not be horrible. But in this case, it's adjusted so that 0 is how well you would be expected to do with just randomly forming clusters, and then the maximum is 100, and we're doing very well. So the bi-encoder has an adjusted RAND index of 91.5. Re-ranking, where we take the closest articles from the bi-encoder and run them through a cross-encoder, does slightly better, but the differences aren't huge. Whereas when you can pair that to n-gram methods, and so looking at how many n-grams the articles have in common, where we've taken the threshold of n-grams in common that you need to be the same from this full day validation data. And so we are kind of, even using the validation data to find a good threshold for the n-grams. But those do not great. LSH, locally sensitive hashing, is a more scalable and efficient version of n-grams. I won't go into the details of that here. Okay, and so we do some ablations to understand what is driving this. And so in the baseline model, we do community detection to remove some clearly evident false positives. So imagine that there's 2 big clusters of articles, and then you just have 1 false positive linking those. Community detection can remove that. But without community detection, it makes a really, really marginal difference. We can do, instead of doing single linkage clustering, we can do hierarchical agglomerative clustering, which is going to matter for the bi-encoder results. And it's a little bit better, but it's not dramatically better, which is good because it doesn't scale well. It's kind of more costly than n squared, and so it wouldn't scale to large data sets. We tried just using SBERT off the shelf, which has not been trained for this task, right? It's been trained for semantic similarity, but, and it does much worse than the model tuned for this task, although it actually does kind of around the same as just using n-grams would. And then we use different loss functions, which actually do not quite as well as our baseline contrastive loss. We can also separate the test set into 1930 and 1974. So now we're evaluating on full day samples, labeled samples from 30 and 74. And the OCR is worse in 1940 because these are much older documents, and you can see that it's kind of a bit worse across the board. In 30 than in 74, but regardless, the neural methods are outperforming the rule-based methods, the n-gram methods, and that's particularly the case as the OCR quality gets worse. Okay, we can also do ablations on the n-grams, and so if you take out community detection, it does make it kind of more noticeably worse, I'd say, than in the neural methods. We can just force every word in the article to be in the dictionary, and we do a bit better, but we still really outperform the neural methods still really outperform n-grams. And then finally, the baseline uses 3 grams, but we can use 4 grams, 5 grams, 10 grams, 15 grams. Actually the 3 grams do the best. Okay, we can use character level n-grams, where instead of the n-grams being words, they're characters. So now we use 10 grams, 15 grams, 20 grams, 25 grams of characters. And again, like, it's not really like making that huge of a difference. It's maybe a little bit better depending on which n you use. And that varies between hashing and n-gram overlap. With n-gram overlap, the baseline is the best. So you can use character n-grams, but that's not going to make a big difference relative to using word n-grams. The neural methods still really outperform n-grams. We choose the threshold for single linkage clustering on the validation set. Kind of analogously, we choose the threshold for what share of n-grams you need in common on the validation set as well. And you can see that with the neural method, the results are relatively robust to using different thresholds. I mean, obviously the cosine similarity threshold matters. If you make it way too low or way too high, it's going to do very poorly. But kind of within reasonable values of it, the results are quite robust. Okay, so those are the baseline results. So just to summarize, the neural methods that are learning this contrastive space where articles from the same wire source are nearby and articles from different wire sources are further apart, regardless of abridgment, OCR errors, regardless of how similar the different articles are, is significantly outperforming methods based on n-grams, where you essentially just say if these two articles have above a certain threshold of n-grams in common, then we're going to call them the same, which is kind of what the entire literature has done. Another question might be, well, like locally sensitive hashing, LSH, is used because it's super data efficient. It runs very quickly. And oftentimes when we're working with text, we have just these massive text corpora. And so how efficient is it to, how costly is it to deploy the neural methods? So we conduct experiments on a 19 gigabyte, 10 million article corpus that is created by applying an object detection model to newspaper page scans. And these experiments are going to use, a reasonably powerful CPU and a single NVIDIA A6000 GPU card. So kind of in the realm of working with text data, I mean, this is an incredibly modest setup. Okay, and so to deploy this, first of all, we need to embed the 10 articles through our pre-trained model. And so that gives us a vector representation for each of these 10 million articles. And then we can use Facebook AI similarity search with the setting index flat IP to calculate the pairwise exact distances between the embeddings. So that is 10 to the 14th similarity calculations. Fortunately, FAISS is insanely optimized, and so it can do that on a single GPU card. Then we build a graph where each of the 10 million documents is a node, and edges connect documents whose embeddings are within the threshold distance, which recall the threshold was calculated on the validation set for clustering. And we use the CUDA graph tools to build this graph. False positives are controlled by running community detection on the graph. And so this bi-encoder method detects over 800,000 distinct reproduced articles. I think very impressively, the average duplicated article was reproduced 6.41 times, which is incredibly similar to what we found in our labeled single-day samples. So when we take this and we apply it to 10 million articles, cluster sizes are not blowing up with false positives. They're staying almost exactly what they are in our labeled data. And so this is breaking down the time required. So most of the time required to deploy the bi-encoder is to just embed the articles. So to take those 10 million articles and pass them through our encoder to get the 768 dimensional vector representation of that article. That takes a little over 8 hours. This is on just a single GPU card. Then we compute the similarity, which requires making 10 to the 14th distance calculations. FAISS is insanely optimized, and so that takes around 3 hours on a single GPU card. Building the graph is essentially, trivial. It takes about a minute, and then community detection is, completely negligible. So the total time to detect which articles came from the same newswire source in this 10 million article corpus is under 12 hours, again, on a single GPU card. With hashing, we run hashing on a CPU. All the widely used hashing libraries are on CPUs, so that takes a little under 4 hours. And then again, building the graph, community detection, which we do on the CPU for comparability, is completely trivial. And so hashing is faster, but the time it takes to get that additional accuracy from the bi-encoder, which is significant, is pretty marginal, again, given this is done on a single GPU card. And so, in short, it's highly scalable. We can take a massive corpus and figure out with very, very high accuracy which articles are the same using deep neural methods, and it doesn't take that many resources to deploy this. We also apply these same methods to the colossal clean crawl corpus, or C4, which is what large language models are trained on. And so this is a massive data set, because we did have limited compute and we had a week to do this, because that's how much time you have to do revisions in this field. We applied this to 2 subsets of common crawl. So we applied it to Real News, which consists of around 13 million digital news articles that were scraped from the internet that are part of this corpus, and a large, actually, part of this corpus that large language models are trained on. And then we apply it to the nearly 100,000 patents from Google's online patent database. So there's around 90,000 of them. And this is the largest single domain in C4. So we don't know the ground truth for these data sets, right? Because with news, there's a timeliness factor. Within a given day, we can be confident that we have all the duplicates, and there's not going to be a duplicated news article when we pool 1930 and 1974 for our test data, right? Whereas we don't have that in C4. There's no good way to know how many times an article in Real News was duplicated without labeling all 13 million of them. I guess we might potentially have the date, but kind of in general, we don't have sort of an easy way to label them. As I said, we also did this in a week, so we don't have ground truth labels. But what we do is to detect, to apply our model off the shelf, and then look at the output and see if we're detecting true duplicates that hashing overlooks, and to see with a random sample also what types of false positives those methods are finding. And so why will we have duplicates? Well, in the Real News data, news aggregators, which tend to make small edits to digital news stories before releasing them on their own sites, can generate noisy duplicates. And you'll see that this is a very common phenomenon. In the patents data, one source of duplicates is noisy translation, as patents are routinely filed on multiple countries, and non-English language patents were machine translated into English before they're deposited in Google Patents. There's also OCR noise for older patents. So in both of these corpuses, we get noise, and it's a very different type of noise. So in the data set that we trained this model on, it was abridgment, from historical newspapers that had to print it in, a given amount of space. It was OCR errors. In Real News, this is digital news. There's no OCR errors here, but websites are churning them out, and they're making edits to them to, appeal to their audience. In the patents data, it's, most of the noise is from things like machine translation. Okay, and so we mostly want to see, well, we have this pre-trained model. Does this apply to other settings, off zero shot, without actually training or tuning the model on these? But these data sets could also be useful in and of themselves. All right. And so, as I said, we apply the bi-encoder off the shelf. We just use the same hyperparameters as are used in our news copy analysis. And we also use the same definition of a noisy duplicate. For hashing, if we applied the same parameters that were used in the news copy analyses, false positives blew up. We detected 40 times more duplicate pairs with hashing using those parameters than the bi-encoder. So this just goes to show how brittle rule-based methods can be. We had labeled data and we found kind of the optimal threshold for hashing on our labeled data, but when we took that and moved it to another domain, it just didn't work at all. And so to do something more reasonable, we just take what Retro, which is like a retrieval enhanced large language model, did to deduplicate C4, and we just apply their parameters. And following GPT-3, we ignore clusters above a certain size. So again, like GPT-3, Retro, like large language models are all deduplicating C4 with hashing. And so we just we're following what they do. Okay, and so this is breaking things down into real news and patents, and you can see how many clusters of duplicates we find in the first column, and you can see that the neural methods are finding a lot more noisy duplicates than hashing, which are requiring kind of exact 13-gram overlap. Of course, as I said, if we applied the parameters that we'd use for news copy, it would have found way more duplicates and way too many. So this is obviously going to be sensitive to the parameters you choose. For this exercise, we're just choosing parameters that have been widely used in the literature on large language models, which use C4 to train the large language model. All right, how many articles in the cluster? There's, with our method, we get way more. Despite the fact that we're getting more duplicates, we did a random sample of the duplicates that were found by the neural net method, but not by hashing, and vice versa. And of the duplicates found by the neural method, but not by hashing, we found that 20% were false positives. The overwhelming majority of those were updated articles, which, kind of depending on your definition, you might actually want to call them duplicates. We just didn't call updated articles duplicates in the news copy analysis, so we don't do that here. But the false positives are kind of, arguably with a different definition could have been true positives. With hashing, actually, most of the unique duplicates that hashing finds that the neural method doesn't find, nearly half of them are false positives. And then you see a similar pattern emerge with the patent data. Okay. And, by the way, I should say, you might be saying, like, why do I care? Like, why does anybody care if there's duplicates in the training corpus for large language models? It's been shown that when you have duplicates in your training data, it's much more likely that the model will just regenerate the text that it's trained on, and that raises plagiarism and privacy concerns. And so that when the large language model is generating text, it's more likely to plagiarize, to exactly reproduce what it was trained on, which is problematic. And people have shown the same thing with stable diffusion, which was trained on image caption pairs, and there's things like photos of Obama, and it will exactly regenerate it or whatever, because there were so many duplicates of those in the corpus. But some of those photos were copyright, so it can also raise copyright concerns when a generative model is exactly producing what it was trained on. So maybe this isn't the biggest concern for economists, and our reason for doing this was we wanted to understand markets for news and how that influences politics and American society more generally. But kind of in the process, we realized, the way that these large language models are deduplicating their corpuses isn't really working great. And we realized there's a literature that can actually have downstream consequences. Besides for that, you might be concerned that examples from benchmarks are in C4. And that this causes test set leakage, right? So test set leakage is when your test set you're not supposed to train on your test set, right? Because that's cheating. But if you have duplicates in your corpus, then you might have the same or a noisy copy of the same example in your training data and your test data. And that's going to give kind of an unrealistic picture of how well your model performs on unseen data because it's not really unseen. And so we looked at duplicates in the training versus the development set for RealNews, as well as duplicates in SuperGlue, which is a common benchmark that also appeared in RealNews. And so we indeed see that, like, in corpuses that have nothing to do with news, there aren't duplicates, and that's like a placebo check, you know. So if this benchmark doesn't have anything to do with news, then there's not duplicates from RealNews, and that, you know, that makes sense. But in the test set corpuses that were news, you know, we're finding a lot more duplicates, and that's, you know, potentially problematic for downstream tasks. So in particular, we took this record set, which is made from news, and you can see that we're finding 519 duplicates, and hashing is only finding 2 duplicates. And when we feed those to GPT-3 and ask them to provide the answer, it's getting the duplicates right more often than it's getting the non-duplicates right, and by a pretty significant margin. And, you know, so I think it's not surprising, but it shows that kind of these test set leakage issues can potentially be something to keep in mind, and another reason why we might want to use neural methods to deduplicate you know, the test set data against the training data. And again, like GPT-3, when it evaluates it, it does deduplicate, but again, kind of using these hashing methods. So to sum up, the study provides evidence that neural methods offer significant performance gains, even on corpora that are significantly different from the historical newspaper data that we trained on. And importantly, these methods are highly scalable with modest compute, which is really important to us as economists because we have super modest compute. And the bi-encoder methods, even when you're working with huge data sets like our 10 million article corpus, they're actually really scalable on a single GPU card, which is pretty amazing. And so these results suggest that neural text deduplication is straightforward and worthy of further examination. I think kind of in the context of this class, if kind of you have a problem where you want to understand whether 2 texts are the same or not, it should be highly feasible to apply neural methods, and it should lead to a lot more accuracy than applying the standard n-gram-based methods. So I'll really look forward to talking more about this paper, about its economic applications, etc., in class on Tuesday. Thanks, everyone, and have a great rest of the weekend.